Today I will show you how to build this procedural setup, meaning you can make changes to it by tweaking some of the inputs and it will update itself accordingly. I'll show you all the steps involved, from generating the necessary curve structure, subdividing it, placing the points around in a ring, scaling those rings, animating them. Then you'll learn how to generate the actual rings from that scaffold structure, thickening them and turning them to 3D moving parts, forming this clockwork tower sculpture. I will start with the points node and create a custom input for the count number. Increase the number to 6. Each point will represent one ring. Let's convert these points to curves. Go ahead and open a statistics window to clearly see what's going on. In its default mode, the points to curve node connects all input points into one continuous curve. To separate it to 6 separate segments, feed an index node into the curve group ID input. Since the index number is unique for each point, every point will become its own group, so this operation will get us 6 curves, one for each point. Before moving on, let us store the index number of each spline into a named attribute called ring index. We'll make use of it later. Observing the final render, you must have noticed that the rings are segmented. The first one starts with 2 pieces and the segments double with every ring going outwards. Currently all the curves have only one point. We'll resample them, but we'll tweak the count value for each ring based on its index number. Connect a power operator into the count socket and feed the ring index named attribute field into the exponent input. Set the base to 2. Since the indices start counting at 0 and 0 squared is 1, the first spline will only have 1 point. Add 1 to the index field number and we're good to go. Store this attribute for each spline into a named attribute called ring divisions. Keep an eye on the statistics panel and you'll see that every spline has twice the points of the previous one. This node graph will get rather crowded, so I'm in the habit of framing the nodes based on their function. You should make it a habit too. It's immensely helpful later on to understand the steps you took to achieve something. Name this frame Generate the Core Structure. It might seem rather strange hearing me talk of rings of splines while seeing nothing on the screen. Trust me, we're getting there. There are a couple of ways you can spread out points in a circle, and I will show you both of them. The first one involves using trigonometric functions. Add a set position node and feed a combined XYZ vector field into the position socket. We'll drive the point's x coordinate with a cosine function and the y coordinate with a sine. Both these functions expect an angle in the range from 0 to a full circle, or 2 times pi, or better still tau. Connect a multiply node into them. At the second input, type #tau. Dividing the point index per spline by the total point count per spline returns us a normalized offset factor along that spline. Remember, I'm using spline parameter index and spline length nodes. These fields get us the indices and total point count per spline. Set this result as the multiplier together with the tau angle. As the point index increases, so will the angle around the circle. And like magic, the circles appear on the screen. It doesn't matter that they are all overlapped. After all, they have all the same radius of 1. Let's spread them apart. Insert a vector scale function and feed an index field into the scalar socket. The index field gets its context from the node it operates on, in this case the set position node. It works on points, so by default each point, each point of the total geometry, is being pushed away from the center based on its index number, resulting in a giant spiral. Insert and evaluate on domain node and set its mode to spline. Now the splines form concentric circles whose radius increases by 1 unit with every iteration. There's just one tiny problem. We only see 5 circles, although we generated 6 seeding points. That's because the circle with index 0 is completely scaled down to 0. To remedy this, add 1 to the index number. There you have it. We successfully generated the basis for our Clockwork tower. Let's animate the circles now. We can do this easily by adding some value to the normalized vector we already calculated. Insert an add operator after the division. Play with the value and see the circles rotate in unison. That's nice. As we increase the factor value ranging from 0 to 1, the angle increases by a multiple of tau. But that's not quite what we want, is it? Analyzing the rendered animation once more, you will notice that each ring going outwards rotates half the amount of the previous one. So instead of adding the same constant amount to the factor each frame, we'll add a different fraction per ring instead. Fraction means division. Let's divide 1 by the ring division named attribute. Slide the numerator value now and see the difference. Each curve rotates half the amount of the previous one going outwards. Why is that the case? Because every ring has double the amount of points, so the fraction value shrinks twice every step. To animate this value and have it loop perfectly, I'll add a little expression into this input. Type hashtag frame divided by frame underscore and hit enter. This will add a driver to this property. We're not done yet though. We need to make some tweaks. If a warning panel pops up, click on the Ignore button. Right-click on the pink colored property and select Edit Driver. In the Driven Property panel, let's focus on the expression we just wrote. Although this is not a tutorial on drivers, I'll quickly run over some basics. The frame keyword is a built-in variable from the Simple Expressions library. It's a small library of keywords and functions that work natively with drivers. It represents the current frame in our active scene. Dividing the total frame number by it returns us a value ranging from 0 to 1 during the whole animation. But frame underscore and is not a built-in variable. That's why Blender triggers a warning, assuming you're typing some Python code into the expression. Ignore it. We're not touching Python at all. Frame underscore and instead is just a custom variable name I chose. To assign it the total frame number, the actual frame underscore and value, we need to create this variable. Click Add Input Variable and type frame underscore and into the variable name. I could have gone with a default name var, but I prefer to name the variables after the property they represent. From the Property Type menu, choose Context property. The default context is our active scene. Now type frame underscore and into the property path input. This will assign our actual scene underscore and value to our frame underscore and variable, turning it into a valid keyword in our expression and finally making it work. Scroll the timeline and observe the property value go from 0 to 1 as we reach the end of our scene duration. It may sound as a lot of steps, but I have found that it's a lot quicker and more efficient than doing it entirely with nodes. We can now lower the number of frames for the scene. I'll go with 100. Wait a minute, you might say. This is not a loop. We can clearly see the gaps jump back at the start of the animation. I know, but if we set the type of splines to cyclic, that illusion becomes real. You could go for a full rotation, but it would be a waste of time rendering all the duplicate frames. These are circles after all. We don't need the set spline cyclic node, it was just to prove my point. Frame this group of nodes and name it Spread Points into Circles and Animate. The next step will be to create the Spiralike Crown of our tower. Append another set position node. We will raise the points up in the Z direction only. So feed a position field into the position socket. Insert a separate XYZ followed by combine XYZ node. Connect the X to X and the Y to Y. Those values don't need to be changed. Make some space. Now it's time to make use of another trigonometric function, the arctangent. More specifically, the arctan2 version of it. Without getting too deep into details, let me explain what it does. It's called the inverse of the tangent function. The tangent is the ratio of the opposite side over the adjacent side to an angle in a right triangle. So in practice, you feed an angle to it and it returns you a fraction. The arctangent function instead needs a ratio and returns you an angle. In our case, we feed it both x and y coordinates and it returns the angle at which each point is positioned around the circle. Feed this result into the z coordinate and have a look at the 3D scene. You see the points forming a spiral-like shape. This creates a radial fall-off effect. Hit play and carefully observe how the points abruptly jump at the end of the loop. It took me a long time to figure out how to smoothen the transition, but the answer is rather easy. Simply add some value to the x coordinate before feeding it to the arctangent2 input. How much should you add? Any value larger than the total number of curves will do. How did I come up with this number? Remember, our circle radius increases by 1 unit with every step. Play with the value as you see fit. The larger the value, the smoother the transition will be. I settled for the count plus 1 over the count. It seemed like a good spot to me. See how smooth the points seem to slide back into the start? Let's raise the whole geometry up above the ground level. Insert a map range node. I'm using Blender version 4.5 alpha to record this video. In this version, new nodes were introduced, among them field min and max. This is an alternative version of the attribute statistics node, which works directly with fields. Feed it the result from the arctangent2 and connect the min and max to the from min and from max sockets of the map range node respectively. Create 2 custom inputs to control the bottom and top height of the tower. Frame these nodes and call them spiraling height. Until now I've been talking about rings, but what we've built so far are not the actual rings, the ones we will render, only the base structure. Think of it as a scaffold for the rings. After all, you can clearly see these are straight lines, no arcs. This geometry is what we will use as a starting point to generate the rings. Add an instance on points node. We'll instance a line curve on every point of our geometry. Realize the instances immediately after. Each new curve will be bent into an arc. Resample the curves. Leave the count value at default for the moment. Now I'll show you the second method of creating circles or arcs. Set position again. Put a position field into the position socket and insert a rotate vector node with a combine XYZ at the other free input. We'll only rotate the points on the z-axis, so leave x and y values at 0. Same as earlier, we'll offset the points based on their normalized 0 to 1 factor along the spline. Of course, not all points will rotate by the same angle. The outer rings, having more divisions, need a smaller angle to form a full circle. Divide the factor by the ring divisions named attribute and multiply the result by tau. Finally, set the instance curve line Z value to 0. Now you can clearly see the staggered arcs in their full beauty, rolling along the spiral we set up for them. Continue to document your actions by framing these nodes and naming them actual rings. Hit play and enjoy the result of your hard work for a moment before jumping to the next step. To add thickness to our arcs, we'll use the Curve to Mesh node. Get a curve line as the profile curve. Obviously the Z-axis is wrong. Zero it out and try increasing the X coordinate instead. X is the right axis, but we won't add thickness this way. The Curve to Mesh node uses the normal of each point to calculate the offset of the profile edge. This method doesn't work in our case. It leaves strange gaps where the rings meet. Have a look from the top and you can see it for yourselves. Set the value of X back to 0. We'll only use the Curve to Mesh node to generate the necessary geometry. We'll scale the inner edges of the rings ourselves. First of all, let's define what the inner edges are. Insert a capture attribute after the curve line before it ends into the profile input. The attribute to capture is the factor. This attribute is now present in all the mesh grids generated from the Curve to Mesh node. To see it, in the 3D view, enable the color opacity overlay. Append a view node to the Curve to Mesh operation and tweak the X input slider up and down. Observe the color of the ring's edges. The ones with a factor value of 1 are marked with a white color. Reset the X coordinate input value. We can now scale one side of the grid inwards. Append yet another set position node and feed it a position field. Our inner edges should have the same height as the rest of the geometry, so I'm separating the X, Y, Z components and recombining them with only the Z copied from the original. Next, mix these vectors and feed the captured vector field as the mixing factor. You see where this is going? The direction of the scale is right. We just need to tweak the mixing factor per spline. Insert a multiply node before the factor input. What is the right value to multiply this factor with so that the rings touch each other's edges but do not overlap? Remember earlier we stored a named attribute called ring index. Add 1 to it and divide 1 by the sum. And there you are. We have successfully created the top cap of our 3D rings. Hit play and see the result. For the bottom caps, simply duplicate the set position node, holding Ctrl plus Shift to keep the connections. For this new geometry branch, insert a vector multiply node. Set both X and Y values to 1, but keep the Z coordinate to 0. This will flatten the geometry to the ground. Now join these geometries. To generate the extruded part, append a mesh to curve node to the original geometry. Keep the mode set to edges. We'll need to generate a curve from the outlines of the rings mesh. The outer edges of each ring are the ones which are part of only one face. Connect a face count field node to the selection input and compare them against 1. The result is a closed curve which we can extrude down using a Curve to Mesh operation with yet another line curve as the profile. Zero out the Z-axis and set the Y to 1 instead. We'll control the height with the new scale input of the Curve to Mesh node. Feed a position vector field into it and separate the X, Y, Z components. Holding down Ctrl, disconnect the noodle from the X coordinate and stick it to the Z output. In the end, join this new geometry branch to the caps. Again, frame the nodes and rename the frame Solidify Rings. This concludes the core of our Clockwork Tower sculpture, but if you follow just a bit longer, I'll show you how to tweak and optimize this setup a bit further. In the 3D view, toggle the face orientation option from the Viewport Overlays menu. You'll notice that the upper cap's face normals point inwards. Let's remedy that by flipping those faces. Also, you can optimize the geometry by changing the ring subdivision so that the outer ones are less heavy. Remember, earlier on, we used the same resample value for all the rings. Let's use the rings count to drive the resampling value. Now subtract the ring index value from it and add a multiplier to the difference. Play with the multiplier value as you see fit. I'm settling down for 4. The important thing is that the outer rings, being twice as short as the inner ones, are now subdivided less, creating an optimized geometry. As a last step, add a Smooth by Angle node to smoothen the geometry normals. This part is optional. A friend of mine was interested in 3D printing this sculpture. I thought of a way to split this geometry into parts that can easily be printed separately. We can split the geometry to instances based on several group ID options. If you want to print each ring separately, use the ring index attribute. You can check this out yourselves, add a separate geometry node, switch the mode to instances, and switch through the instances based on their index number. Otherwise, if you wish to print each ring piece on its own, travel back the node graph, add the frame Generate the Core Structure, where we stored the ring division attribute, and store the point index as a new named attribute called Pieces. Using this attribute as group ID will split each ring piece to its own geometry. The geometry we're talking about is made out of 3 separate parts, the top and bottom caps, together with the hollow extruded part. If we merge these parts by their point proximity, the geometry might collapse because the rings are tightly gathered. But we can now merge each instance separately using a For Each Piece zone. Set the mode to instance and insert a merge by distance operation inside it. This whole geometry is still one object generated by the geometry nodes modifier. You can see that in the outliner. To split each instance into its own object, go to the Object menu. From the Apply submenu, choose the Make Instances Real command, and in a few moments you'll see the outliner populated with 1 new object per ring piece. And that's all I wanted to show you. I'm sure you can drive it on your own direction from here now. If you're interested in the scene file, I've posted a link to it in the video description. Thank you for following till the end. You'll hear from me again soon, I hope.